Hello, everyone. My name is Mathieu Bouchard. I am the product manager for surface eddy current array products at Edify Technologies. And the goal of this video today is to introduce you to a new family of ultra flexible probes that we call the P-Flex. First of all, let me show you what the probe itself looks like. So as you can see here, the coil sensors in this type of probe are printed directly into the flexible PCB, into the flexible board. So this allows us to build these ultra flexible probes that are extremely thin and that can be bent in a number of different orientations. This technology of printing coils into flexible into flexible boards has been around for a number of years. But the reason why we're launching this product now and not 10 years ago is that the technology of printing copper into flexible boards has advanced significantly over the last few years, to the point where the coil sensors that you see on the screen here are pretty much as performant as traditional pancake coils that are handmade with copper wire. And the reason behind that is that now they are able to print copper in a very, very dense way, so that the coil sensors that you have here are very dense, made with a very high number of turns. And this translates into more current flowing into those coils, more energy into the magnetic field, and more energy into the eddy currents that will be transmitted into the material. And having those higher energy currents in the material significantly reduces the noise and increases the signal that you get from small surface indications. So the overall performance of detection is significantly better now with those type of probes than it was even 10 years ago. So using the most modern printing technology, we can now address very complex geometry because we are able to insert these thin probes into almost any type of gaps and grooves and tight corners or surfaces that simply have strong band radius. Just to give you a few numbers here, those probes have a thickness of only 0.2 millimeters. That is 8,000 of an inch. So as you can see here, extremely thin. And in terms of minimum bending radius, we're talking about 2 millimeter here, or 80,000 of an inch. And this is a bend radius that you can reproduce any number of ways. So you won't be damaging the probe at all as long as you keep it over 2 millimeter bend radius. So this probe comes in three sizes. The one that you have here on the image is a small model, so small coil sensors. We also have a medium and a large model. The difference between them, they each have exactly the same number of coils. They each have 32 coils. The difference between small, medium, and large is the size of those sensors. So for example, the large probe has more than twice the coverage of this one that you have on the screen here. So having larger sensors first of all, brings more coverage, brings more surface being inspected in a single pass. However, the drawback to that is that having larger coils also reduces the resolution. So you won't be able to detect as fine and as small of a defect with a large probe compared to this small one here. So if you have a look at our probe catalog, there's more precise numbers to help guide you between which of the three probe models would be ideal based on the coverage that you need and based on the smallest flaw that you need to detect also. One of the key points of the P-Flex probe, as you can see here, is that it is detachable from its cable adapter. So the cable adapter here is sold separately from the flexible probe. It has a standard array connector for connecting to either the ready or the hectane. And at the other hand here is where you connect the flexible part. So the probe comes with an Allen key in order to remove the cover and install the probe. So this is not something that you will have to do often, obviously, but the point of making the products modular like that is that if an accident happens, if something gets damaged during an inspection, it can be either the cable getting cut by accident or one of the coil sensors being damaged from a rough surface or a cutting surface. If you have to replace a component, at least you won't have to replace the entire thing. You can just detach the flexible part and replace whichever of the two components is damaged. So right here you see the array connector here and here. This is very straightforward to connect. Before I do that, I just want to have a word on about the accessories that are provided with the probe. So the first one here, you see on the screen the layers of protective peak tape. So the advantage of the flexible probes is that they can be installed in any type of custom holders. So you could decide to build this probe and use it as kind of a building block to install inside a custom holder with a very specific geometry. Now, if you do that, you will want to benefit from the thinnest probe possible with the best curvature capability possible. But if the goal is to use this probe as a standalone and kind of just use it as an iFlex probe with your fingers on the coils and scanning a surface like this, in this case, then we strongly recommend to use the protective tapes, install them on the surface, and create this protection between your sensors and the surface being inspected. This will make your probe much more durable, it will last longer, and you will be able to scan much longer, much more volume of inspections with a single probe. It comes with a bunch of them, so don't hesitate as one gets damaged or worn out. Don't hesitate to just peel it off, replace it with a new one. Here I have a second probe where I have installed one of those layers of tape. Obviously, this makes the probe very slightly thicker, but it maintains its very good performance of strong curvature and flexibility. Now, the second accessory that comes with the probe is this little layer of foam. Again, this is completely optional. You don't have to use it, but this can help if you're using the probe as a standalone without any type of probe holder. This can help to apply an even pressure along the length of the array. So if you press only here with your fingers, you can still have some bend and some flexibility, making the probe not perfectly in smooth contact with the surface. But when using the foam like that, it has a sticky side so that you can stick it onto the PCB. When you will use it on the surface, even pressure, more stable scan, easier to perform your inspection. Now let me connect the probe to the cable adapter. I will then install the cover and we'll connect the probe to Magnify and to the ready and have a look at the data. All right, so I have now connected my probe to the ready. First thing you see in Magnify is that the probe is recognized here at the top right of the screen. It shows the probe name. So now we just need to find the setup file that corresponds to that probe. Make sure that you're using Magnify 5.2 or a more recent version of the software so that this way you will have the proper setup added to the default master list. So when you open the default master list, there will be a new category named pflex, and in there you will see 3 setup files, one for the small, medium, and large probe. So simply select the one corresponding to the probe that you have. In my case here, I'm using the probe D034. This corresponds to the small model of the probe. Before I go any further in the software, just want to have a look at the part that we will be inspecting. So this is a very straight plate of aluminum with a series of notches here and a series of drilled holes here to represent small pitting on the surface. Now the probe, the cable adapter at the back here, you see there's a bracket. It has, again, removable screws so that you can move the bracket sideways if you want to, if there's any restriction on the surface you're inspecting. This gives you a bit of flexibility on the encoder positioning. So this is a standard surface adapter that you can clip right onto this bracket at the back here. So you have your spring-loaded wheel that will record the position of each indication that will be detected. Going back to Magnify, I will move to the front stage, and the first thing I will be doing here is a liftoff calibration. So I go to the Calibration tab, Liftoff Assistant. I make sure my probe is in contact at a clean location of my plate. I will null the probe there and acquire data. Now I'm simply doing a liftoff curve like that. So if we have a closer look at this shape of the liftoff signal, let me switch back to the full view. What you see here is that it is a very usual shape of signal. We have a very straight line with a hook at the tip that corresponds to a transmit-receive topology, which is what our probe is using here. So the idea of the liftoff calibration, as always, is to bring this curve to the horizontal, pointing to the left, like this. And we'll want to repeat the same thing with the transverse signal. So with this probe, like almost all eddy current array probes today, have both axial and transverse channels. The axial indications will be displayed at the top in the axial C-scan, and the circumferential or transverse indications will be displayed at the bottom here. Now my liftoff is well calibrated. I can close this window and I am ready for my inspection. I will simply scan the notches and the small drilled holes and have a look at what the data is. So once again, I null my probe on a clean spot, start the acquisition. And stop. Now I was scanning mostly transverse indications, so we can have a closer look at the transverse view at the bottom. So let me switch to a layout that displays only one C-scan and one impedance plane. So if we zoom on the smallest of the notches here, we set our cursor directly on the small one. There's not really any surprise here. We have the type of signal that we expect from this kind of EDM notch indication. So in aluminum, around 15 degree of phase, 2 volts, very typical signal. So the point here is just to show you that the signals we're getting with this printed probe is very, very similar to any type of ECA signal you would be getting with a conventional array probe with pancake coils. Let us move toward the small drilled holes, small fittings. So here, same type of signal, a little bit of a stronger phase here because we have some volume, but essentially what you would expect with this type of probe in aluminum. Here, I was not using any type of filter, any type of probe holder. As you saw, it was just my hand in contact with the probe, making sure we had good signal. One word on the frequency of those probes, because this is very important to consider. The flexible P-Flex operate at very high frequency. This is one of the limitations of those printed coils. They operate in this case at 1500 kilohertz, which is very high. For surface breaking detection, this has no impact. This is the perfect tool to detect like little indications like those that are breaking the surface. However, it is very limited in terms of penetration. This should not be used to penetrate a thick layer of stainless steel or a thick layer of aluminum and detect flaws on the other side. We have probes specifically for this. We have iFlex probes that go low frequency that are great for that. The point of the PFlex here is really for surface breaking defects at high frequency. So right here I have this uh, part with a strong curvature. So when we look at this part, this is not something that we could have addressed with any other type of eddy current array probe that we offer in the catalog. This is much too small to bend an iFlex over, and there's nothing else really that could inspect even such a simple cylindrical surface. Now with the PFlex here, I'll just remove the encoder for now because it won't be needed here. As you can see, the PFlex can wrap around this surface very, very well. This is what it was designed for, to wrap around or to bend to surfaces with this type of curvature. So in Magnify, we will go through the same process of first calibrating the liftoff, and then we'll do our inspection to try to find some small defects in there. So liftoff calibration, as always, you set the probe in contact. Let me put it a little bit lower to make it easier. Right here. You open the liftoff assistant, null the probe, and acquire liftoff. Now we're doing it again because we're not inspecting the same material. This is not aluminum anymore. This is something else, and we want to recalibrate for this reason. So very quickly here, we rotate this liftoff slightly upward. Same thing here. We can close that assistant. And we'll also want to remove the encoder because we don't have the geometry here to inspect with an encoder. So we will be using the clock. And one last thing I'll do is I will add some filters to help alleviate some of the noise I could have from the probe not being in perfect contact or having some liftoff noise during my scan. This is exactly what those median filters are used for. I can complete, click finish, and perform my scan. Now here, obviously, it would be much easier to build a small holder to help stay in contact. I'll do it with my fingers because I don't have this holder prepared. But with with 3D printing being so widely accessible, I think probes like this are a great opportunity to get one of those and then install it into different holders. You could have one 3D printed holder specific for this diameter. Then you take the probe off it, install it in a new holder with a for a smaller diameter, for a larger diameter. So just having this single eddy current probe installed into swappable holders can help really inspect a lot of different geometries with a single instrument. Okay, so null, acquire, and we go. I'll stop here. So the big line at the end is my liftoff. Let's focus on the rest here. You can see I found at least one flaw that is quite obvious here, the little red dot. This is probably just a small surface pitting from corrosion on the surface. So once again, 18 degrees, typical flaw signal that we can expect from a usual conventional probe. So as I was saying just a moment ago, it can be quite cost effective to reuse the same printed flexible probe into a wide variety of homemade 3D printed holders. So that way, using a single probe, you can inspect a lot of different components without having to purchase a custom probe for each of those geometries. However, it's not always easy or feasible to do that. Sometimes the surface is so complex, has such complicated curvatures, or is such in a restricted axis that it can make more sense to have the probe manufacturer build the custom holder. Um, it's something that at Edify we've always been happy to work on. The probe customization, I think we have built a strong reputation around it, being able to customize eddy current array probes into any shape and size that is required. And this is something that remains true with this new technology. In fact, having access to those printed coils adds even more capabilities to what we can do in terms of customization. And I have a good example here of one custom probe that we have built recently for this with this technology. It is a probe for rotor slot inspection in gas turbines. So the component to inspect is this with this very specific shape. We call it the dovetail shape because of the geometry. So the probe we've made uses the flexible array here. You see all the coil sensors. This is essentially a custom-made version of the P-Flex. We made it longer with up to 128 channels. The probe is installed on a spring-loaded shoe to make sure it is always in good contact with the surface. And as mentioned earlier, it is also protected with a layer of PEEK to protect it from the surface. This is something we always use with those probes. So the flexible part is embedded once again into a modular system. You've got the cable here that can be detached just by removing those 4 screws. And on the other side here, you also have a 2-wheel encoder that can be detached using the 2 screws here. So the encoder, again, will ensure that we position our flaws very precisely. So let's have a quick look at the data that we're getting from this. This is a very straightforward inspection, just a piece of puzzle that you insert into the slot. And from there, it is simply a matter of sliding it into the slot. So very, I would say very smooth sliding, very easy to use. It's really just pushing the probe. So we will first null on the clean surface at the beginning, press start, and slide the probe into the slot. We can now stop the acquisition, have a closer look. And here, once again, we're not using any type of median filter, any type of custom process. This is really just the raw data coming out of that probe and displayed into a Syscan image. So very good signal to noise ratio, very good uniformity between the coils also, because being able to print the coils automatically like that brings a lot of uniformity. Each coils in an array of 100 coils will be exactly identical to its neighbor. And that makes it another advantage of using the printed technology. So excellent signal to noise ratio. Those smallest flaws here on the left are about a half millimeter deep by half millimeter long, and they are detected quite nicely here. So just once again, a good example of where Edify can offer engineering services to help integrate this new technology, integrate those flexible probes into perfectly tailored custom probe holders. Just in conclusion of the video here, just to summarize our capabilities with, as I said, probe customization. So we can make those P-Flex, those custom printed probe up to 256 channels. This is the highest number of channels we can reach with our instruments. As I was explaining, this tool brings more flexibility to what we can do in terms of customization. And there's various approaches that we can use. For example, here, the probe I showed on the left has the coils outside of the geometry. We can also choose to put it completely hidden inside of a box, so inside of a holder. Here, it's very important to be careful that to keep this thickness here very, very thin, to keep the coils, of course, in close contact with your surface being inspected. Now, I found this quite interesting. We were able to compare the performance of our probes with a probe that was, I think, 25 years old. So just the same technology that they used 25 years ago, but with much less density of the coils, much less performance in terms of signal to noise. Also, as you can see here, the signal on this little notch is all crooked with the big tip at the end, which is typical of absolute coils with those type of probes, and unfortunately decreases the signal to noise. So when we compare with the performance of our new Edify's new P-Flex probe, we have much brighter signal, much stronger signal to noise also, and a stronger phase as well. That helps detecting those type of flaws. I'm finishing here with the probe catalog. As I said, three types of probes: small, medium, and large. And the cable adapters at the bottom, we have two different ones. The one I was using today was for the small and medium sizes. There's another one for the large probe size, so a separate adapter. All of them have only 32 coils, which makes them fully compatible with Ready 64 and Ectin 364 channels. And as always, the probe customization is always available. If you need any type of custom holder to use these probes, please get in touch with us. We'll be happy to help. So I hope this video has been useful, if anything, informative on our new product, our new P-Flex product. If you have any question, feel free to reach out directly to us. We'll be happy to answer them, do a remote demo, or just have a look at more data from this technology. So thank you. Have a good day.